For the second theorem, we have that Pn is a sequence in a metric space. And what we want to show is that actually, if it converges, then there is a unique limit. But we say it in a funny way. We say, well, let me suppose there were two limits. Pn converges to P and Pn converges to some number P prime. Then P and P prime must be the same. Okay. So one way to show this would be by contradiction, assuming that P and P prime were different. But we are not going to do it that way. What we are going to do is constructive. So what we are going to do here, the geometric idea is because there is convergence. Oops. Then there is going to be a ball around both these limits, P and P prime, with a small radius. And then we are going to see that the points in the sequence, at some point, they are going to be very, very close to both P and P prime. And we are going to use a triangular inequality to estimate the distance between P and P prime in terms of the distances between P and Pn and P prime and Pn. Okay, this will be clear in a moment. So here, first thing we are going to do, because we have convergence involved, let's say that epsilon is a positive number that is given to us. Okay, and then by definition, because Pn converges to P, then there exists a number n positive such that if n is bigger or equal than n, capital N, then the distance between Pn and P, I'm going to need more space, is going to be less than epsilon. Okay, this is the definition. Any epsilon you give me, this is the definition of convergence of Pn to P. But similarly, we have that Pn converges to P prime. So we can pretty much copy the definition, just the only change, oops, is that now I write P prime in place of P. And here, the information we have is this one here. You see, in the picture I drew, we have that the distance between Pn and P prime and Pn and P is going to be less than epsilon. Okay, they are within an epsilon distance. But now I was saying, if I want to estimate the distance between P and P prime, because I want to show they are the same, what I'm going to show is that they are as close as we want. Okay, so by the triangular inequality, this is the distance. This is less or equal than the distance from P to Pn plus the distance from P prime to Pn. And this, each of these is less than epsilon. So the sum of the two is less than 2 epsilon. Okay, and here we conclude, because epsilon was arbitrary, we can let epsilon go to 0 and conclude that the distance between P and P prime is 0, so they must be the same one, because this is one of the properties of a distance. Okay, and that would be it. That would finish the proof. Now, one thing I want to tell you, because usually in analysis proofs you see this a lot, is that usually you like to find here epsilon instead of 2 epsilon. So what we are going to, once you do the proof the first time around, and you get some quantity like it's like 2 epsilon or 23 epsilon, doesn't matter, you say, okay, let me start backwards, and let's say I want to find epsilon here. Let me actually keep the color code. If I wanted epsilon here, then you go back and you are like, oh, I need epsilon halves for each of these distances. So that means that I need to apply the definition of convergence with epsilon halves instead of epsilon, okay? Remember, the definition says for every epsilon, every number you want, so you could pick half of the epsilon you were given. So this is sometimes we see this a lot in analysis, and it's a little puzzling in the beginning because you see like epsilon halves, epsilon thirds, and all that. Doesn't matter, just do the proof with epsilons, and if in the end you feel that you got like an ugly number, 3 epsilon, 27 epsilon, whatever, just go backwards and fix the epsilons.